Anand Krishna sir, you're the co-host. Thank you,
Yes,
Imtiaz
yes.
sir.
Thank you.
Shall we begin, sir? Shall I ask Shivraj to give the recap of previous
Yeah,
class?
yeah, yeah, sure.
Good morning, children. Shivraj.
Uh, yes, ma'am. Yes, ma'am.
Okay, good. Shivraj, you can
So,
begin.
yes, sir. So last week sir taught us about. First, we started with Monty Hall problem, which we had a recap on the last week, and yeah. So sir told us. I mean, the question was about if we have to if we are given three doors and one of them contains a car behind it, and the other two contains code. Is it beneficial? And if we choose one door at the beginning, is it beneficial to switch or not? And we actually saw that it was beneficial with the proof. And it was more clear when we looked at large number of doors instead of just three doors. And after that, we discussed about Simpson's paradox, which involved two doctors and both of them doing one heart surgery and band-aid removal. And we looked at the table of their success and failure, and based on that we calculated some metrics. Yeah, this is what we discussed in the last class.
Right. Thanks.
Yes, sir.
So to start with, good morning to all. So today we'll be looking at a major example called Gambler's Ruin. And this example would show up again once we reach the topic of Markov chains. So this is a pretty important one to understand well. And this model is going to be reused for a few classes after this. So to start with, I mean, as Shivraj pointed out, we covered Monty Hall and then the Simpsons paradox, and they had important techniques that might come into use once you start solving problems. So we'll begin with Gambler's Ruin today. So the setup is as follows. So you have two gamblers, and what they do is it's a step-by-step procedure. They keep trading back and forth. I mean, they keep gambling back and forth. And what I mean by back and forth is they keep gambling by betting $1. Okay, at every round. And this continues till one of the gamblers is ruined. And by ruined, I mean he goes out of cash. Okay, to make it more concrete, let's call these gamblers A and B. And let P be the probability that A wins a round. And each round is independent. So the results depend in a way such that the money goes on reducing, I mean, or increasing. Other than that, what happens in every round is independent of the previous round. So we call Q as the probability that B wins a round. Okay. And this remains, P and Q remain constant in every round. That's what I mean. Now, so the game ends when A or B goes bankrupt. And let's assume that we have N dollars to start with. And what I mean by $10 to start with is the money that A has plus the money that B has is adds up to N. Okay. And the question is, what is the probability that A wins the whole game? I mean, the same question can be posed as what is the probability that B wins the whole game? But let's just stick with A. And this is the same as the probability that B is ruined. Because yeah, we'll maybe not go there. But what is the probability that A wins the whole thing? Okay. This is our question. And to start with, A starts with, so since N is a total, let's assume that A starts with I dollars. And so B starts with N minus I dollars. Okay. Any questions? So is the setup clear to everyone?
Hope all of your children are able to send yes messages.
Okay. Okay. So with this setup, we need to solve the probability that A wins the whole game. Now, the idea to solve this problem is what is known as a random walk. We won't go into too many details here of what is a random walk and so on, but we'll see these again later in the course. But for now, let's consider this line. And it's an integer indexed line segment. So let this line represent the amount of money that's being gambled. So it can range from 0 to n, and A starts at position I, 1, 1, so on up till n. Okay. So here, so you are trying to model this problem as a random walk. So what is the random walk here? So A starts at point I, and if A wins the round, A gets $1 because we have assumed that by betting $1. So every round involves betting $1. Okay. So if A wins a round, he or she goes to I plus 1. Okay. And this happens with probability P. And we have defined P as the probability that A wins a round. Okay. Now, the question is what happens when you reach 0 or n? So 0 and n are absorbing states. Once you reach these states, you don't move anywhere, and then the game is over. So the goal is to reach one of these states. So if A reaches 0, then he loses. What we need is the probability that A wins. So A finally should reach n, and that's when the game ends. Okay. So is the overall idea of a random walk clear? So the random walk is over this integer line segment, and A can move. I mean, similarly, B can move to some position, but we are only concerned with A right now. So that's why I've only represented A. Similarly, you can do it for B. So any questions? So is the setup clear? Okay, cool. So now the strategy to solve it, to solve this random walk is to use a conditioning of events. Okay, so we call it conditioning on the first step. So what I mean by this is just that. So if you are in state I, so let's call 0 to 1 as n states, and if you are in state I, and that means that you are starting the player A is starting with $I. Okay, and now what you need to calculate is a probability that A wins the whole game. So let us call Pi to be the probability that A wins. I mean the whole game when A starts with $I. All right. Now we need to somehow find the RHS of Pi. So how do we model that? So now with probability P, A wins that given round, and then P with P, I moves to I plus 1. I mean, A moves to I plus 1. All right. So with probability P, this is just the probability that A wins given A starts at I plus 1 plus with 1 minus P probability A can lose, which is just Q. And this is just the probability that A wins the whole game given A starts at I minus 1. Okay. By definition, this is just P into Pi plus 1 plus 1 minus P into Pi minus 1. Is this clear? Is this clear for everyone? Like how this equation works out? All right. All right. So now what you can see is this equation is a recursive equation in the sense that Pi depends on I plus 1 and I minus 1. So we need to solve this somehow. All right. And to make it more clear, so when the state is between, let's I and minus 1, this is the equation that we need. But as soon as we reach P0, something happens, and Pn, something happens. Can you look at the definition and tell me what the values of P0 and Pn are? So what is P0? I mean, you don't have to solve this equation for that. It's just looking at the definition. Yeah, exactly. P0 is just 0. And what is Pn? Pn is 1. Exactly. Nice. So with these sort of terminal conditions, we have to solve this recursive equation. So I'm not sure how many of you have taken a discrete math course, but if you've taken one, you might have come across what is known as a difference equation. So a good reference for this would be, there's a textbook called Grimaldi for discrete maths. I think it has a chapter on recursive equations, solving recursive equations, and it has this method for solving difference equations. So these equations are generally known as difference equations. It's just, I mean, you might have seen the continuous form of this, but it's just there are these differential equations in continuous mathematics. It's similar to that, but it's just discrete here. So it's known as a difference equation. So knowing how to solve such equations comes up very often in discrete systems. So we'll only be seeing how to solve this equation specifically, and I'll show you a general template for it. But to know more about it, you will have to go and refer the textbook or any online sources. So, I mean, just Googling this will give you a Wikipedia page, and it has many methods. All right. So the technique is basically this. So you guess what PI is, and you usually set it up as x to the x power I. All right. Now substituting this in the equation, what you get is xi is p into xi plus 1 plus q into xi minus 1, because q is just 1 minus p. All right. Now you divide the whole equation by x to the I minus 1, because that's the lowest term. So what you end up with is x equal to px square plus q. Now this is just a quadratic equation, so you just apply the minus b plus or minus root of b square minus 4ac by 2a. Okay, so everything clear till now? This is just solving a quadratic equation. Is this clear till now? Yes. Okay. So once you have this, you will see this term under the square root, which sort of looks complicated and hard to understand. But if you look at it as a, I mean, if you can take out the square root and put a square inside the square root so that it cancels out the square root and the square, it'll be nice. So let's try to do that. And we do that by completing the square. So this is just this 1 minus 4pq. I just substituted for q. So now this is an equation in just p square. All right. And this is exactly same as 1 minus 2p whole square. So what we get is x equal to the first term is, okay, let's not directly run. Let's just see 1 plus or minus 1 minus 2p by 2p. Okay. So if you solve for this, what you're going to get is q by p, which is just 1 minus p over p and 1. Okay. Everything fine till now? Okay. So let's just proceed. So if p not equal to q, then how you solve this is you don't have repeated solutions. So if p equal to q, there are two solutions and both are just one. So you have a quadratic equation with a repeated solution. That's not the case if p not equal to q. So if p not equal to q, you write the solution of a differential equation as follows. A is some constant. A and B are not the agents here. So let's just use some other C1. C1 is some constant. It's an arbitrary constant which you'll have to figure out using the terminal conditions. It's Q over P, the first solution, raised to the power I, plus C2 raised to the power into 1 raised to the power I. So this is a general form of a solution of a difference equation when the roots are not repeating. We'll see the case when roots are repeating, but this is the general form. All right. Now we know in addition to this that P0 is equal to 0. All right. So you just substitute for I in the above equation. Sorry, C1 plus C2. And Pn is 1. And what you have is C1 into Q over P to the power n plus C2. Okay. So from the first equation, you know that C1 equal to minus C2. Substituting it in the second equation, you will get that it's just 1 minus Q over P the whole to that. All right. So these are the boundary conditions. All right. Is everything clear till now? So we have seen how to solve this differential equation when Q is not equal to P, and you saw that C1 is 1 over 1 minus Q over P to the whole to the n, and C2 is just a negative of that. Okay. Is everything clear till now?
Is it clear, children?
Okay. So now we'll see the case where P is equal to Q. So what do you mean by P is equal to Q? P and Q are probabilities, and Q is 1 minus P. So if P is equal to Q, what is the value of P? What is this value? Yeah, exactly, half. So now we need to solve this for half. So we have a repeated solution since P is equal to Q. Then the general form of this is gonna be like this. So C1 is some arbitrary constant. First solution. I mean, there are two solutions which are repeating. So this applies to all the repeating solutions. Okay. So you might have repeating solutions and then distinct solutions for a difference equation. So what I'm gonna write applies to repeated solutions, and you can just add up the remaining distinct solutions if there are any to in general to solve a difference equation. But if you have a solution repeating two times, then the first term does not have the I term here. So if you look at it, there's an I term here. That's the difference, and I is same as this I, which is same as this I. So this is the general form of the equation. So if you have, say, three repeating, one is repeating three times, the root one is repeating three times, you will have same these two terms, and then you will have another term with an I square, and so on. So that's how you write the general form of difference equation solution. We have seen the case for both repeated solutions and non-repeating solutions. So now we have to we have to find C1 and C2 in this case as well. So if you plug in the values, you'll get C1 is 0 and C2 is 1 over n. Okay. Is this clear? Okay. So now what is PI? So we have figured out PI in both the cases. This is exactly this. If P not equal to Q, and this is just I over N if P is equal to Q. All right, so how did we get this? So P is equal to Q is just this case, the second case that we saw. And you just substitute the values that you have found for C1. So C1 is 0. So the first term cancels out. C2 is 1 over N. And you have a N sitting there. And that is 1 to the I. All right. So that's how you get the I. And then you have that C2 is 1 over N. Is it clear? So similarly, if you plug it in for P not equal to Q, you will get the same solution. I mean, the solution that I've written here. Is this clear for everyone? How to solve a difference equation? Okay. Okay. Cool. So now the question is, what is the problem? I mean, what is the probability? So this is a question for you guys. What is the probability of a draw? So one of you will have to give me the answer for this. Okay, let's look at a specific case. If P equal to Q, what is the probability for a draw? So there are two players, and we have only calculated for, I. So player I starts with, sorry, player A starts with I dollars, if you remember, and player B starts with n minus I dollars. And my question is, what is the probability of a draw? No, 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 no. Okay, what is a draw? Draw happens when you either won't win and you won't lose. So this is the winning probability. What is the losing probability? Okay, what is the probability that B wins? What is the probability that A wins? And from that, you should be able to guess what is the probability of a draw. So if there are only two situations, that A wins or B wins, then draws cannot happen. Or you should show that A and B can win together. Okay, just look at P equal to Q case. So don't look at this case for now. Just look at this case. All right, so what is PI? So PI is defined as the probability that A wins if A starts with I dollars. Okay, so I mean, you can just make it B wins with B starts with I dollar and minus I dollars, and that will just become B. All right, so what will be PI for B in this case? Can someone tell me what is PI for B? So if we calculate the same thing for B, so B starts with n minus I dollars. Exactly. So that is n minus I over n. So now the probability that A wins is I over n. The probability that B wins is n minus I over n. So what can you say about the probability of a draw? Quickly, can someone tell me? Okay, so A wins with the, yeah, exactly, it's 0, because A wins with probability I over n. B wins with probability n minus I over n. When you add both of these together, it's equal to 1. So that means the probability of there's that there is a draw is 0. So probability of draw is equal to 0. Cool. So the same thing would apply to P not equal to Q as well. And yeah, so please verify that. The same technique would work. We just have to add both of those, but adding them might look complicated if it is not. All right. Now, yeah, that's it for the example part of today. Now we'll move into more theory. And we'll be starting with random variables today and then proceeding with that for, I think, 2-3 weeks, I guess. Now, what is the motivation for the random variables? So now, say here, for example, A having I dollars, I mean, A starting with I dollars was a difficult thing to represent. So let's say here in the same problem, gamblers doing problem, we wanted to represent the money that A has after, say, some rounds of the game. And mathematically speaking, you don't have a way except to just write that A is at state n minus k after k rounds. So other than that, there's no way to represent these statements till now. So what mathematicians have come up with is this notion of random variable to help you with that. And using event notations, I mean notation, events as notations gets hard. This is our motivation. For example, another example would be, say, let's say we have two dice, and we need to represent the sum of two dice. All right. So how do we represent that? So we don't have a method to do that till now, and random variables helps us with that. So let's see what random variables. Okay. Now, calling a random variable is actually a misnomer, because there is nothing random about random variables. A random variable is basically a function. It's a function from the sample space omega to the real line. So this is what you have to remember, even if you don't get anything else. I mean, this is very crucial. I mean, people confuse this all the time. So this is something you have to just store it in your head. It's just a function from the sample space to the real line. And how you see it is as follows. So you have the sample space, say S, or here omega, and little omega is the outcome. It's an outcome. Okay. Now every point in the outcome is the input for the random variable. So let's call the random variable as x. So x is a random variable. Okay. So in that case, x takes the input as omega and spits out some value on the real line. All right. This is what a random variable does. This is all that a random variable does. And the randomness comes from omega. So this omega is the outcome of an experiment, a random experiment. So you don't know what omega it would land up at. But once the omega is fixed, x of omega is always fixed. There's no randomness in calculating x of omega. The only randomness is the randomness for the input of x. Is the idea clear? This has to be very clear, because everything that we are going to do from now would use the concept of random variables. Everything till the end of the course. Is the idea clear? Okay. Now let's move on. So you can think of random variables as a numerical summary of some aspect of the experiment. So think of random variables. So we'll denote random variables using RV capital usually, and random variables are usually denoted with capital letters in textbooks and so on. So think of a random variable as a numerical summary of some aspect of the experiment. Okay, this I say in the sense that, say you throw a die and you see the outcome as say 5, and you throw another die and you see the outcome as say 3, but our random variable is defined to, so let's make it more concrete. So x is the sum, is the random variable that indicates whether, I mean, x is just the sum of outcomes of two thrown. All right. So in that case, x takes values from 2 because the minimum value for each die is 1. So 1 plus 1, 2, and it can go up till 6 plus 6, which is 12. Okay. Is that fine? So depending on the outcome of the die throw, the sum is going to change. So that's the randomness. But once you know the outcomes, the output of the random variable is fixed. Okay. Just point out that again in the notes, randomness comes from the experiment. Once the outcome is fixed, there is no randomness to find the value of a random variable. Okay, this is very crucial to understand. Now let's start with the uh, famous Bernoulli distribution. All of you would be already familiar with it. So Bernoulli distribution. So we'll formally define what a distribution is later. We'll define this later. But yeah, I mean, all of you would already know what a distribution is, but we'll define it formally later. But a random variable x is a Bernoulli has a Bernoulli distribution. So I'll use Bern to shorten distribution. If x takes two values, 0 or 1, and the probability that x equal to 1 is say p some number between 0 and 1, and probability that x equal to 0 is exactly 1 minus p. Okay, and note that writing this way, that x equal to 1 is an abuse of notation. Actually, anything inside the probability, so how did you define probability to be? The probability function p, this p, was defined to be from the subsets of the sample space to some value between 0 and 1. So x equal to 1 should represent a subset. And this notation does not capture that fact, but what I really mean here, and I mean, this is standard notation, but what it really means is the set of all outcomes omega such that x of omega is 1. So when I write x equal to 1, this is what I mean. I don't want to write this over and over again. This is standard practice. No one writes this event. So this is an event. All right. And the probability function should always contain an event inside it. So when it says it contains a random variable, you have to define an event associated with the random variable. And the event is the set of all omegas where x of omega is 1. Is it clear? So all these things are just minute details, but they can confuse you when you see a problem. So that's why I'm explaining it over and over again. So did you understand why writing x equal to 1 is not the right way? But still, that's the standard practice. So I also have to follow it. But x equal to 1 is just an event which corresponds to the set of all omega such that x of omega is equal to 1. Is this clear? This has to be very clear. I won't repeat these things again. So, all right. Can I see more yes or no's? Okay, fine. Now, this is the definition of a Bernoulli random variable. All right. Similarly, we'll see what a binomial random variable is. And it has two components. So the Bernoulli random distribution, or the Bernoulli random variable x only depends on the value small p. Small p is some value between 0 and 1. All right. Now for binomial, there are two parameters. One is n and p. I'll say what is n. So when you think of binomial, this is what you think, what you should think. So this is the distribution of number of successes in n small and independent Bernoulli trials. All right. So basically, you can think of n coin tosses, n independent coin tosses where, yeah, you know what is independent. So n independent coin tosses, and you are just counting the number of successes. So this is what the Bernoulli random variable does. So when I say x is a Bernoulli binomial, sorry, when I say x is a binomial random variable with parameters n and p, p is same as before, the small p in the Bernoulli distribution. And I repeat the Bernoulli experiment n number of times. So to have a running example, when you think about binomial, it should be just n coin tosses. It can be n coin tosses. So with probability p, the toss results in a head, and with probability 1 minus p, the toss results in a tail. And you repeat this n times independently. That's what I mean by a binomial distribution. All right. Now we'll see what is known as a probability mass function. Okay. And this is how you describe a random variable. So this is the way you describe a distribution, or you describe the associated kind of random variable. So when I say the probability mass function, I mean the probability mass function of a binomial distribution here. All right. Which is exactly what this captures. So this is the PMF of Bernoulli P rand. Bernoulli P, the only parameter is P. And when I say binomial, I mean this probability that x, which counts the number of successes of n repeated n coin tosses which are independent, with success probability p for each coin toss. What is probability of x equals k? All right. And what values can k take? Can someone tell me what values can k take depending on the definition? Can someone tell me what values can k take, or what values can the random variable x take? Can someone please tell me what values k takes? So what is the definition of x? X is just the number of successes of n independent trials. So how many successes can there be? Maximum n. So what values can x take? Exactly 0 to n. Right. So this something that you should understand properly. So okay, so we are doing n coin tosses, and let's think that we need k successes, which means that we need k heads, say for example. So how many different ways when you're doing n different trials can you have k successes? When you throw n, I mean when you have n coin tosses, to have, yeah, exactly, n choose k. Yes. So now in choose k ways you can have k successes. All right. Now we need to calculate the probability. Now that you have these k fixed, now what is the probability that k independent trials? So these are independent. Note the fact that these are Bernoulli trials, which I mean by saying this, I mean they are independent. Note the point. So for having, so we have k successes. What is the probability of that happening? So probability that let's order these k successes. So we have picked k successes. Now let's call them 1 to k. And the first of those k successes happens with probability what? P, exactly. Now you have k of them, and these k of them are independent. So what is the probability that you have k successes? Just k successes. And choose k. Not to the power p. So n choose k is fixed. So what does n choose k mean? N choose k is just picking k successes. You have picked the k successes. Now I'm talking about probability, not the counting part. So you have k successes. So first success happens with p probability. Second also happens with p. So you have k of them, and they are independent. Exactly, p to the k. And what happens to the remaining? So the remaining success, I mean, the remaining should be failures. So you have exactly k successes. So you should have n minus k failures. Yeah, exactly. 1 minus p to the n minus k. Okay. So this is how you define the PMF of a binomial random variable. I hope this is clear for you. So I mean, you can go ahead and take this as the definition of binomial distribution, but understanding it is better. So you repeat the k Bernoulli trials and you derive this formula. All right. Now, yeah. So one example for this would be, say you have 3 successes and the rest of them are failures. So let's say n equal to 7, which means that you are doing 7 coin tosses. Okay, maybe I should make 1, 2, 3, 4, 5, 6, 7. So yeah, you don't need this. So you have n equal to 7, and this is the outcome of a binomial experiment. And let's case 3 here. So this is one sample instance of binomial distribution. I mean, sample instance of a binomial experiment. All right. Now let's see some properties of binomial distribution. So if x is a binomial random variable with parameters n and p, and y is another binomial random variable with parameters m and p. So what do I mean by n and m here? So n is the number of times the first experiment is done. M is the number of times the second experiment is done. but it's done with the same coin. That's what I mean by fixing P for both X and Y. Okay. Now the question is, what is the distribution of X plus Y? Can someone guess what is the distribution of X plus Y? I mean, just understand the meaning of what I've said till now and think about what actually is happening. So when I said about the binomial distribution, I asked you guys to think about coin tosses. Now X counts, I mean, I'm not going to repeat what I said, but X is a binomial random variable and Y is a binomial random variable. What is X plus Y? I mean, I would like at least 3 answers, 3 people guessing some answer. Yeah, exactly. So it's binomial n plus m comma p. It's binomial n plus m comma p. So the intuition is very simple. So X counts the number of successes when you do n trials. Y counts the number of successes when you do m trials. So X plus Y is the total number of success when you do n plus m trials. And you are using the same coin, so P remains the same. So X plus Y is X plus Y is distributed according to the binomial distribution, and the parameters are n plus m and P. Right. So the proof is just exactly what I said. So consider n plus m trials. These are Bernoulli trials, so independent and so on. So X is the number of successes for the first n trials, and Y is the number of successes in the next m trials. So total number of success is X plus Y from n plus m trials. So it's this, and it's the same coin P. So P remains the same. P is same. All right. Now, this is one way of thinking about the binomial distribution. Let me present you guys with 3 different ways, and then we'll wind up the class. All right. So when you talk about binomial distribution, this is what I mean. X is distributed according to binomial n comma p. Okay. So first one is the one that we just saw, the intuitive way of looking at it, which is just X is the number of successes of n independent Bernoulli P trials. The P is important because the P is same here and here. Okay. Now, what is the next way to look at it? The next way to look at it is the sum of Bernoulli random variables. Okay, this is another important technique that is often used in computer science. So you may see a binomial random variable and you might have to do something with it. So what people do is just split into the Bernoulli random variables, because why not? So you are conducting n Bernoulli trials, and xi here is a Bernoulli with parameter p. And okay, IID is an important concept. And what IID means is they are independent. So x1 through xn are independent random variables. I mean, I've defined independence for you. Think about it. So x1 through xn are independent random variables, and they are identically distributed. So when I say IID, this is what I mean. So independent, everyone knows. Identically distributed just means that all of them are Bernoulli here. So x1 is Bernoulli, x2 is Bernoulli. Everything till xn is also Bernoulli. So when you have a sequence of random variables x1 through xn, and when I say they are IID, this is what I mean. Okay. Is this clear for everyone? So x1 to xn are different random variables. They are not the same random variable. Okay, there is a, when I say IID, I only mean that they have the same distribution. Depending on, I mean, they can be, for example, x1 can be just the sum of two dice. X2 can be the difference between the mod of the difference between whatever the dice output, and so on. As long as the distribution of the sum and the difference is the same, then it's fine. Then you can say that they are IID. If they are not, then they are not IID. That's all I mean. So here x1 and x2 are different functions, but they have the same distribution, which is Bernoulli here, and they are independent. Okay. So we have defined independence of events, and you know that we can map a random variable to an event, and that's how you check the independence of random variables. We'll come to that later, but I mean, that should be the easiest way to think about it. Fine. Is this, what about the case when the value of P is different in both X and Y? All right. So then they are not IID. Good question. Oh, sorry. So your question is, when I say Xi is, this P changes? Is that what Shivraj meant? About the formula express. Can you unmute and just speak it out?
Yes, sir. So
Yeah.
so in the above, you mentioned that x plus with binomial of like x is binomial of n comma p, and then y is binomial of m comma p. Then if you add both of them, you get binomial of n plus m comma p.
Yes.
I thought, what if it's n comma p and m comma q? Then
yeah. So then we don't have this. We have to numerically calculate it.
yes. I was just thinking. I was just thinking if there's some general formula.
No, good question. Yeah. I haven't worked it out. I mean, you can just work it out.
Yes.
So once you know the PMFs, you can work it out. So
Yes.
I will show the third method. So the third method of, I mean, the three ways to think, the third method is gonna be exactly that. So I'll show you how you can do that. So I think by that, the answer would be clear. Is that fine?
Yes, sir.
Okay, cool. So what I thought is this. So if P changes here, can they be IID? They can still be IID because they are still identically distributed, because the distribution is same, and they are still independent. So yeah, that's what I meant. Is it clear for everyone else? Okay, can I see a few more yes or no's? Okay, cool. So let's just see the last method and then wind up. I don't think I'll reach the point where we'll calculate x plus y, but this is the third way of looking at it, which is just the PMF. N choose k, p to the k, 1 minus p minus k. This is what we have seen. So this is the third way of looking at it. So these are the three ways in which you can interpret a binomial distribution. And what Shivraj asked was a good question. So try to figure out what is x plus y when x and y are distributed differently, but they are both Bernoulli. So x comma y, I just write it as before, is binomial and comma p, and then y is binomial m comma q. And p and q have no relation. All right. Cool. So I'm not sure if I have more time. So Jasma ma'am,
Yes, sir.
so I've taken up. Uh, I mean, I think I've just finished 1 hour. Can I take a few more minutes if that's
Yes,
okay?
sir. Yes, sir. Please carry on. Not a problem at all.
Okay, fine. So I would just like to show you guys how you do the x plus y thingy. So this is a homework, and what I'm going to say is for the condition I showed before. So I'm just going to put it as p. All right, and we'll see the three ways of calculating this. So the first way we have already done it. The intuitive way, we did the calculation and showed why it's binomial of n plus m comma p. So this was the answer. So x plus y is distributed as. All right. Now let's look at the second way. Second way is just representing x using the corresponding Bernoulli random variables, and y can also be represented using Bernoulli random variables. All right. So now what do we do? X plus y is just x1, add all of these together. I is equal to 1 to n, I is equal to 1 to m. And this is sum of n plus m Bernoulli trials. And all of them are based on the same coin. So Bernoulli P. Okay. So n plus m Bernoulli P trials. The P is fixed. So this is exactly the definition of a binomial n plus m. Okay, I hope that's clear. So this is almost same as the first way to look at it. Now, let's see how you do it otherwise. So this is the third method, probability that x plus y is equal to k. Now we have conditioning to a rescue again. So what you do is you assume that you know the value of one of the random variables. So what you need to calculate is x plus y. Now seeing x plus y together is kind of complicated and you don't know what to do. So let's just fix x to be j for now. Okay. And by law of LOTP, law of total probability. I mean, this is just conditioning. So this is just probability of A intersection B. All right. And I'm splitting it up. So X can take values from 0 to K. So X can take values from 0 to K, and I've fixed it at J for just seeing it. Now what we can do is, we know that X and Y are independent. So X and Y, okay, should have mentioned it before. Independent random variables. Now, when you fix the value of x at j, what is the value of y? What is y here? So what can I write the first expression as? So you know that x is j and the sum is k. So what can you write? What is the probability same as? So this expression, what can you rewrite this as? You can rewrite this as something like this: y equal to exactly k minus j. All right. Now you know what is probability of y is equal to k minus j, right? So it is m choose k minus j into p to the k minus j into 1 minus p to the m minus k plus j times n choose j. I'm just applying the formula of binomial distribution here. Okay, so x, the first is so this whole term is just the formula for the distribution of y. And okay, what I mean by the formula is just this. I'm just plugging in the value of y is equal to k minus j, and this is what you will end up with. And if you simplify this, what you can see is p to the j and p to the k minus j cancel out to give p to the k. All right. Now let's call 1 minus p as q, or whatever, 1 minus p. Now if you add up the exponents, what you're gonna get is the j cancels out and you will get m plus n minus k. So this is similar to the expression for a binomial random variable with m plus n trials. If you just pattern match it with the formula. And now we have to figure out what this part is. M choose k minus j times n choose j. Okay. So we can take these two terms, the p terms, outside because the summation is only dependent on j. So it's just p to the k 1 minus p m minus m plus n minus k summation m choose k minus j times n choose j, and j runs from 0 through k. All right. So can someone tell me what this is? And we have seen this in one of the first few classes. In the combinatorial identities section, like we had seen many such complicated formulas, and we had these story proofs. So do anyone remember what this expression turned out to be? So there was a story associated with it. So it was that you have some number of people and then you want to form two teams. So you wanted to form a team from two such sections. So you had girls, boys. You wanted some number of girls and you wanted some number of boys, and say you wanted to form a team. So that was the story I used there. So what would the summation become? I need a single expression for this whole summation. And we had exactly seen this. Okay, I mean, you can always, I mean, you know the answer, guys. So you guys already know the answer for what is x plus y. So x plus y is a binomial random variable with what? It's a binomial random variable with parameters n plus m and p. So you should be able to just reverse engineer that. You don't even need to know this actually, but yeah. So you already know the answer. Can someone calculate it fast and then tell me what it is? So you know that x plus y is a binomial random variable. Find out the binomial distribution for x plus y, the formula, plug it in, and you will see these two terms there. And there will be something instead of this. What is that? Oh, no. So what I'm asking is, so you know that x plus y is a binomial random variable because we have already seen it with the intuition. So plugging it with the binomial formula, like, so you know that x plus y is a binomial random variable. So you can plug it in this formula. So if you plug it in this formula, what would be this term? Okay. So you will see a variation of this with different parameters, right? Can you guys? Yeah, exactly. N plus n choose k. Yes. So n minus p, n plus n minus k, n plus n choose k. All right. So this is the answer, and by this, we have proved that x plus y is a binomial random variable with exactly the distribution with parameters n plus m and p. Okay. So this is how you prove the sum of two random variables. I mean, find the distribution of two random variables. And okay, now that you have seen this in a reverse engineering way, do you guys remember the story? Like, do you see the connection between these two? Yes or no? Okay, go back to the notes, check what this is called, and let me know in the next class. So this had a name. I had given a name to this identity. So yeah, find it out and let me know. Good. So that's all I wanted to do today. So next class we'll see a few properties of PMFs, and we'll define what is known as the CDF of a random variable, cumulative distribution function. And after that, we'll go on to see other types of distributions other than Bernoulli and binomial. Okay.
Thank
So,
you, sir.
yeah, that's all for today's class. Thank
So
you.
next Friday we'll meet. Instead of Saturday, it will be regular Fridays only
Yes, ma'am. Yeah.
at 9 o'clock. And the
Yes, ma'am.
same URL.
Sure, sure, sure.
Yes. Thank you so much, sir. Have a nice
Thank
day.
you, ma'am. You too, ma'am.
Thank you.
Thank you.
Bye.